Hey everyone, welcome back to Everything Mathematics. Today we're going to see how to solve trigonometric equations by putting pretty much a lot of what we have learned about trig, especially when it comes to trigonometric functions, the unit circle, identities. We're going to put all that together to solve equations. I have another video in this channel also in terms of solving equations, and I will make sure to link that in the description below so that you can watch it if you wish. Before we start, however, we're going to start with some prior knowledge. I'm going to assume that you feel very comfortable with this Pythagorean identity, that you also feel comfortable with these reciprocal identities, and that you feel comfortable with these double angle identities. These are the identities that I plan to use in the two examples that I have chosen here for the examples in relation to solving equations. Another thing is some helpful tips when solving equations. When solving these type of equations, keep in mind that it may be really useful to change any trig expression into the basic trigonometric functions. For example, if you have cosecant, consider changing that into sine. If you have secant, consider changing that to cosine. And cotangent, change that to tangent. Technically, this can be really helpful. Also, if you have fractions, consider getting a common denominator in order to simplify. If you can substitute an expression in the equation with an identity, that could end up being extremely helpful as well. And if you have quadratics or if you have common factors, think of factoring. Always factor, factor, factor. This question right here is asking us to solve the following equation in the interval from 0 to 2 pi. When I look at the equation, I see that in the first term, I have the sine of x plus pi over 4. In the second term is the sine of x minus pi over 4. Well, immediately I am thinking of these identities right here. The identity for the sine of the sum of two angles and the identity for the sine of the difference of two angles. Again, I am assuming that you already have knowledge of these identities, and I have another video in the channel that shows how to derive these identities. I will make sure to link that video in the description below. In order to proceed, I will think of x as angle A and pi over 4 as angle B. Same thing over here. X is A, pi over 4 is B. And then I'm going to be applying these identities right here. And every A and B will be replaced with X and pi over 4. Let's go ahead right now and expand the first term. And then we're going to do the second term. So with the first term, we're going to have sine x times cosine of pi over 4. So I am applying the identity here directly. I'm applying the first one for the sum of the two angles. And then plus, here we're going to have sine of pi over 4 times cosine of x. So all this over here corresponds to the expanded form of just this first term over here. Okay, applying this identity right here. Now we're going to go ahead and do the second term. We're going to expand the second term, and I'm going to do that in green, different color, so that we can keep track of everything. So now plus sine x cosine of pi over 4 minus sine of pi over 4 times cosine of x. All of this equals to -1. So this is what we have. Now, simplifying. I want you to notice immediately that this term right here is identical to this one. I will go ahead and underline it. Actually, no, in fact, I will highlight it. So I am thinking of this term right here is identical to this one, but they have opposite signs. In other words, this one is positive and this one is negative. That really means that I can cancel those two terms. So now the leftover will be considerably simpler. It is going to be sine x times cosine pi over 4, and then over here, plus sine x times cosine of pi over 4 equals to -1. Now look at this. These two expressions are identical, and they're both positive, so I can go ahead and add them. I can combine them. Remember, this is like having a plus a equals to 2a, right? That's how we add two like terms. So in this case, we are going to have 2 times sine x times cosine pi over 4 equals to -1. Much better. Now what we have to do is to evaluate cosine of pi over 4. Well, I want you to remember that pi over 4 is a special angle in the unit circle with coordinates √2 over 2, comma √2 over 2. And also remember that cosine corresponds to the x value of these coordinates. So then that means that I can go ahead and replace all of these over here with √2 over 2. So we're going to have 2 times sine x times the square root of 2 divided by 2 equals to -1. Simplifying allows me to cancel the 2's, and then I'm going to go ahead and move the radical in front because it now becomes the coefficient. So I'm going to have square root of 2 times sine x equals to -1. Now, my goal here is to isolate the variable, in this case, sine x. That means that we're going to do that by dividing both sides by the square root of 2. So on the left, that will divide out, and we are now going to have that sine x is equal to -1 over the square root of 2. And so that you recognize exactly what we have, I'm going to go ahead and rationalize the denominator by multiplying top and bottom by the square root of 2. So now this is going to give me that sine x is equal to minus square root of 2 divided by 2. And I want you to notice immediately, just look at the ratio, just the ratio. This number right here, square root of 2 over 2. If you notice, let me take you to the left. This corresponds to this special angle pi over 4. So that becomes our special angle, our reference angle, pi over 4. And then in the unit circle, I'm going to go ahead and work here on the left. Right here, I have a lot of space here. And we will identify the quadrants where sine is negative. So just imagine. Sine is negative in quadrants 3 and in quadrant 4. Again, the circle will be going through here. I'm not going to bother drawing the circle. We know that it's there. Let's just focus on the terminal sides of the angle. So one angle in standard position is in quadrant 3, and then the other angle is going to be in quadrant 4. And because now I know that the reference angle is pi over 4, both of these angles are going to be multiples of pi over 4. In particular, the one in quadrant 3 will correspond to 5 pi over 4. Let's write that down. So x in quadrant 3, I'm using Roman numerals for quadrant 3, that will be 5 pi over 4. And then the angle right here in quadrant 4 will correspond to 7 pi over 4. And just like this, we have exactly the two solutions that are within the restricted domain from 0 to 2 pi. This second example is asking us to solve the following equation and then to give that general solution. So in the previous problem, we had a restricted domain and we found only two solutions within that restricted domain. Here, they're not asking us, or they're not giving us a restricted domain. They're asking us for all the solutions possible, the general solution. But before we get there, let's look at the equation. I see that I have 2 sine x on the left and 7 minus 3 cosecant x. And as I said at the very beginning of this video, that whenever we have cosecant, what we want to do is to rewrite it in terms of sine. That tends to be a pretty helpful thing to do. So let's go ahead and do that. I'm going to write 2 sine x equals 7 minus 3 divided by sine x. Now that I have everything in terms of sine, my ultimate goal is to isolate sine to see if I can solve. But before I get that, I want to get rid of this fraction. And in order to do that, what I should do is to multiply both sides of the equation by this denominator. So I'm going to go ahead and do that. The left side and the entire right side will be multiplied by the denominator that I'm trying to get rid of, by sine x. And then the same thing over here. This will be multiplied by sine x. So then, on the left side, we are going to have 2 times sine squared x. On the right side, it is super important to remember that you have to multiply every single term by sine. So this is distributive property. That means that this factor multiplies every single term that is within brackets. So then we are going to have 7 times sine x minus 3 over sine x times sine x. Right? So notice again, here it is. Sine x multiplied 7 and sine x multiplied 3 over sine x. But what is really nice now is that sine x will divide each other out. And now we are going to have 2 times sine squared x equals 7 times sine x minus 3. And I am hoping that you can already see that we have a quadratic in terms of sine. And the way to solve a quadratic equation is to move everything to one side and to leave 0 on one side of the equation. So I'm going to go ahead and move everything on the right towards the left, because this is where I have the expression with the highest exponent. That means that we're going to have 2 times sine squared x, that will stay on the left, minus 7 times sine x plus 3 equals to 0. So here is the quadratic equation. And we need to remember that every time that we want to solve a quadratic equation, we think of factoring or the quadratic formula. But in this case, this will be factorable. Now, another tip that may help you is to momentarily let a simple variable like u replace sine x. Sometimes this is really helpful for the brain. It helps you simplify the problem and just focusing on factoring without the noise of sine. So imagine that I replace sine with u. That means that we will have, let me do this on the side right here. We would have 2u squared minus 7u plus 3 equals to 0. So much nicer, considerably simpler. And now we try to factor the quadratic. That means that we're going to have 2u and u minus 1 and 3. Just a quick check to make sure that everything works. That looks good. And now what I'm going to do is I'm going to come back over here and write down my factors. But now instead of u, I will replace sine x. So sine comes back. So here is the first factor. That means that we're going to have 2 sine x minus 1 and then sine x minus 3. Those are my 2 factors. Now I'm going to set each factor equal to 0. That will allow me to generate 2 simpler equations that hopefully will be easier to solve. So from here, we're going to take 2 sine x minus 1 and set that equal to 0. And also sine x minus 3 equals 0. So for the first one right here, we're going to go ahead and isolate sine x. That means that sine x will be equal to 1 over 2. And over here, we're going to do the same thing. Sine x will be equal to 3. Now, I'm going to tackle this one because hopefully this is obvious that this equation has no solution. And that's because sine x can never equal to 3. Because hopefully you remember here that sine x is always bounded between it's always bounded, I should say, by -1 and 1. So sine x is always between -1 and 1. So it is impossible for sine x to ever be equal to 3. The highest value that sine x can achieve is 1, and the lowest is -1. So as a result of that, I will conclude that there is no solution for this particular equation. Okay, so for this particular one over here, no solution. So now the one that I have to analyze more carefully is this one. I will go ahead and move here on the right side. I have a bit of space. So sine x equals to 1/2. And just as we did with the previous problem, we're going to think of the unit circle. And we're going to go ahead and identify the 2 quadrants where sine is positive. Sine is positive in quadrant 1 and sine is positive in quadrant 2. And again, I'm not going to draw the entire circle. You can imagine that it goes like that. So now what I want is this angle right here in the first quadrant and the angle in the second quadrant. I want you to notice how sine x is equal to a special ratio, to 1/2. 1/2 is one of those special ratios that corresponds to special angles in the unit circle. So I know that I'm dealing with the special angles like, to remind you, pi over 4, pi over 3, pi over 6, pi over 2. Which one is it going to be? Well, remember that sine x always corresponds to the y value of those points. So in this case, I know that this will be equal to y. Remember that those points are always on the unit circle. So for example, here, I would have such a point, and I already know that the y value will be 1/2. That means that the x value will have to be equal to √3 over 2. Again, I am assuming that you have quite an extensive knowledge of the unit circle and these special angles and special coordinates. So then that means that this particular point will correspond to the special angle pi over 6. I'm going to write this over here, pi over 6. which means that we already found the first angle, the angle in the first quadrant. So the angle in quadrant 1 will have a measure of pi over 6 radians, which really means then that the angle right here in quadrant number 2 will be also a multiple of pi over 6, which is going to be precisely 5 pi over 6. So x in quadrant 2 will be 5 pi divided by 6. So now these are the two angles within one revolution. But keep in mind, they ask for the general solution. Because the two angles, the two terminal sides of the angles form a V, I'm going to have a general solution for each of those two angles. So the general solution, and keeping in mind that the period of sine is 2 pi, the general solution for the first angle will be pi over 6 plus or minus 2 pi times n. And just to remind you that pi or minus is there because I am thinking of n as a natural number, just the counting numbers, 1, 2, 3. And when we want to get that general solution, we want to get all coterminal angles with pi over 6, positive and negative angles. So by putting plus or minus, I capture everything. And then for the second general solution in quadrant 2, we are going to have 5 pi over 6 plus or minus 2 pi times n. And now at the end, I'm going to say that n is a natural number. So here are the two general solutions for this particular equation. Okay, friends, I hope that you found this lesson helpful, and I hope that by now, after having watched the second video on solving trigonometric equations, you feel more confident that you can tackle some of these problems on your own. You have seen exactly how we apply identities, how we go back to the unit circle, and we use all of that knowledge that we acquired in the past, and how we now put it together here to be able to find solutions, whether these are solutions within a specific domain or whether these are general solutions. Equations are different. Every equation will be different. So the only way that you will be able to improve and to solve these equations with accuracy and with good speed is with practice. So I cannot emphasize how crucial it is for you to practice and how crucial it is for you to memorize the identities so that whenever you need to recall the identities, your brain can immediately find the identities that you need. Let's put it that way. Anyways, I hope that you keep practicing. I hope that you keep enjoying. And until next time. Bye, everyone.